Okay, people, I'm going to be looking at some of the derived quantities in this video and showing you how to derive them. I want to start with area. The area of a plane figure, the area of a shape, plane shape, is defined as the product of two lengths. So let's call the symbol A. Area, the unit is derived from multiplying the length and the width or the breadth, and that gives you, it's like multiplying the units. The unit of length is a meter, unit of breadth is a meter. So meter times meter gives you meter squared. So that gives us the unit, the SI unit of area, being meter squared. That's the SI unit of area. You can use other units like kilometer squared, as if the area was the length and the breadth or the width were expressed in kilometer. Okay, we can also express area in centimeter squared and also in millimeter squared. Okay, then the second, I want to look at the volume of a solid shape. That is, the symbol is V. It is defined as the base area of the shape or the solid shape multiplied by the length or height of the shape, like the volume of a cuboid, the volume of a cylinder. Now the base area has the unit of meter squared because area is the product of two lengths. Product of two lengths is area, and the height is also in meter. So that gives me the unit of volume as meter cube. And meter cube is the SI unit of volume. You can also have volume in centimeter cube. You can have it in a millimeter cube, and so on and so forth. Even in liters. So this one applies to capacity of a container. It's always expressed in liters. Okay, so the third one, I want to write this density. The symbol is this, call that rho, a Greek letter. Density has been defined as the ratio of mass of a body to its volume. That is density. And then how do we derive the unit of density? We start by writing down the unit of mass, which is in kilogram, divided by the unit of volume, which is meter cube. This can also be written as kilogram per meter cube, or can write it as kgm minus 3. And then you can also express density in grams per cm cube. That's another unit, alternate unit of expressing the density of a body. And this is very, very important because sometimes in exam, in questions, they will not even tell you that these parameters is stated, is density. But when looking at the units of the quantity given, units of the parameter that is stated in that question, you will know that this is density and nothing else. So that gives the density and the unit. Then I want to talk about speed. The speed of a body, the symbol is V, is defined as the ratio of the distance traveled to the time taken. So how do we derive the units of speed? From the symbol, from the definition of speed. Distance is expressed in meter, time in second. So this is my meter per second, meter per second. This line is same as this line. Or we can write it as meter multiplied by second raised to power minus 1, applying the rule of indices. We also express distance in kilometer per hour, speed in kilometer per hour, and so on and so forth. Okay, speed and velocity, they have the same units. While speed is distance over time, velocity is displacement over time. The fifth one, I want to write acceleration. How do we derive the unit of acceleration? Another derived unit. The symbol is A. Acceleration is defined as the change in the velocity of a body over time taken for the change. So just at the way the quantity is defined, the same way was to arrive at the unit of acceleration. Velocity is meter per second. I told you earlier that speed and velocity has the same unit over another second, which is for time. So how do you express this? How do you simplify this? Meter per second, which is written as meter per second squared, or meter per square second, which is also written as ms minus 2. And so maybe wondering, how come meter per second gives this? This second here has a power of 1. If I apply my rule of indices to s raised to power minus 1 and s raised to power 1, it's like I'm dividing two indices. If you divide two indices, this divided by this, the rule says that you must subtract their powers. You take one of the letters s, you subtract the power minus 1 minus this one. So this is already having a negative index. This minus is because you are dividing the two indices. That gives you s raised to power minus 2, which is this minus 2 here, the unit of acceleration. You can also have acceleration in kilometer per hour square or centimeter per second squared. Cm per second squared can also be used to express the acceleration of a body depending on the question. Okay, I want to talk about force this time around. The symbol is F. We define the force acting on the body as the product of its mass, that is the mass of the body, and the acceleration that is imparted to the body. Now, here, the SI unit of force is in Newton in honor of Isaac Newton. You see that now? But we can also have the SI base unit of force. SI base unit of force. How do we do that? The derived unit of force in terms of base unit, in terms of the fundamental unit. We start by writing down unit of mass as kilogram and the unit of acceleration here as meter second raised to power minus 2. So this gives the SI base unit because the unit of force is now given in terms of only the base units. And what are the base units again? Kilogram, meter, second, ampere for electric current, Kelvin for temperature, mole for amount of a substance, and candela for luminous intensity. Okay, so that's how we arrive at the units of a force. How about work done or energy? You know, energy and work done, they have the same unit. Whether it is energy or work done, they have the same unit. And work done is defined as the product of force and the distance moved by the force. Okay, so we have the SI unit of work done as the joule in honor of Mr. Joule. You know, this man did a lot of experiment and research on this in this field of heat energy in physics. Okay, so we have to write Newton here as we can also have it as Newton meter, which is another way of expressing work done. Newton for force and meter for distance. But in terms of SI base unit, what's the SI base unit of work done? SI base unit of work done. Now that of force is already given us as kilogram meter per second squared multiplied by distance is meter. So it's like we are multiplying this by this, meaning that we are going to multiply this meter by this meter because those are the two like units. So that gives us meter squared S minus 2. So this gives the SI base unit of work done, kilogram meter square per second square, because meter multiplied by meter, the rule says that when you multiply two indices, these two meters, their power is 1. So 1 plus 1 gives us 2. Okay, let's look at power. What will be the units of power, the derived unit and the SI unit? So power is defined as work done, the rate at which work is done, work done over time, and the work done is joule. Okay, this one derived unit of work done, joule. Time is second, so we can give work done unit of joule per second. Okay, that's another way of expressing work done. That's the that's the unit of power, joules per second. But the SI unit is what? The watt is the SI unit of work done, you know, in honor of James Watt. It's named after that popular scientist. So work done can be given in joules per second as well. And then the SI unit is the watt. How about the SI base unit of work done? Base unit. Here we have the SI base unit of work done as kilogram meter squared S raised to power minus 2 divided by, we divide that by S, which is also the unit of time. So when we divide these two expressions, that is to say, we are now dividing, we are rather kilogram meter squared. When we divide S minus 2 by S raised to power 1, the rule of division says when we divide two indices, subtract their powers. That gives us minus 2 minus 1. That gives us S minus 3 as the SI base unit of power. Okay, that's the SI base unit of power. So I've gone through the derived quantities of some of the quantities we have in physics, starting with area. We have that here. We have how they are derived, how the unit is derived, the SI unit column, and then other units that can be used to express these derived quantities. We see that for volume, for density, for speed, for acceleration, for force, for energy or work done. Both have the same units. For power. Then how about for pressure? So I'm going to show you how to derive the units of pressure. Now the pressure acting on the body, or pressure that is exerted on the surface, is given by the force acting on the surface over the area of the surface. So with this expression or definition, we can derive the units of pressure, the SI units, Newton for force over meter squared for area. So this is also written as Newton per meter squared, or can write it as Nm raised to the power minus 2, applying the rule of indices. We can also use Pascal to express our pressure. Pascal, it's also accepted as SI unit of pressure. Okay, now let's look at another unit apart from pressure. Let's look at momentum. Momentum is like talking about the mass of a body in motion. That is momentum, mass of body in motion. So it is defined as the product of a body's mass and its velocity. It's a vector quantity, just as the definition, the unit follows the definition. Mass, that is kilogram, then the velocity, that's a unit of meter per second. So this gives the SI unit of momentum, kilogram meter per second. Again, we can still say that 1 kilogram meter per second is equivalent to the Newton per second. So sometimes we can give unit of momentum as Newton second. Okay, impulse and momentum have the same unit. Impulse is the product of the force acting on the body and the time during which the force acts. So impulse, product of force and time. The unit is still Newton second, meaning that the impulse on the body or impulse received by body is the product of the force and time, which has the unit of Newton second or kilogram meter per second. I want to talk about add this one, that is specific heat capacity. I don't know if you have heard of this before. It's a symbol, a quantity in physics rather, and is defined as the quantity of heat energy over the mass of the body and the temperature of the body. So this is the expression for specific heat capacity. We want to derive the units of specific heat capacity. The SI unit is derived from this expression that defines the specific capacity. So we have joule for heat energy over kilogram multiplied by Kelvin. You can see that now. So most times some write it as joule per kilogram per Kelvin, or simply joule kilogram raised to the power minus 1, Kelvin raised to the power minus 1 as the SI units of specific capacity. So maybe I'll give you this to do as an assignment to find the SI base unit. Okay, you look for the SI base unit of specific heat capacity. That is, you know what the joule is. The joule is equivalent to kilogram, we derived that before, meter squared S minus 2. That is the joule, then over kilogram, kilogram and Kelvin, okay? Kilogram and Kelvin. So kilogram cancels kilogram. So what you have left here is meter squared S minus 2. When this Kelvin goes up, take it up, the power becomes negative. So you can see this is the SI base unit, expressing the unit of specific heat capacity purely in terms of base units or quantities. Okay, now let's look at charge, electric charge rather, electric charge, electric charge. Now electric charge, the symbol is Q. Charge is defined as a product of current and time. So the SI unit is the coulombs in honor of Mr. Coulombs. Okay, C is the essence of charge, but the base unit is ampere for current, second for time. So the column C is equivalent to ampere second. Okay, then also we have the potential difference number 13. Let me write here potential difference. Potential difference, that is to say the work done taking unit charge from one point to another in an electric circuit. So the symbol is V. It is defined as work done over charge. So work done is expressed in joule, charge in coulomb. So this joule per coulomb is the derived unit of potential difference. It's also equivalent to the volt, which is the SI unit of potential difference, the volt. So I can write here V, volt is the SI unit of potential difference. And you can also find the base quantity, sorry, base unit. of potential difference. Base unit, work done is kilogram meter squared second minus 2 over charge is current times second. So when you evaluate this, it gives you kilogram meter squared. Now this A, that's the denominator, has a power of 1. When it goes up, the power changes to negative 1. Then this is s minus 2 divided by s raised to power 1. That will give you s raised to power minus 3. Following the rule of indices, that when you divide two indices, you subtract their powers. However, if you are asked to find or derive the unit of resistance, the symbol is R. Resistance is defined as the potential difference between the terminals of the conductor or the resistor over the current flowing through the conductor or resistor. Okay, so we have here volt per amp as the derived unit of resistance, but the SI unit is the ohms. The ohms is the SI unit, and the symbol is this omega, the uppercase letter of omega, the last letter of the Greek alphabet. Okay, so that is the derived unit of. We can also have the SI base unit of the ohms. Potential difference is a kilogram meter squared s minus 1 and s minus 3. So you divide that by current, which is ampere A. So when we express that, you have kilogram meter squared s minus 2 s minus 3, because this is 1, this divided by this, when this other one goes up, it becomes minus 1. That gives you minus 2 as the SI base unit of resistance. Okay, so maybe I'll complete this in the next video. So we've seen about 14 of them, derived quantities, and how to have their unit, the SI unit, and then the SI base unit.